Okay, I think it's time to get started now. Welcome, welcome everybody to the June meeting for the Friends of the Observatory. If you haven't signed in already, just put forward out there, just please sign in if we can keep track of how many people we've got at each meeting. Tonight we got, I think, really interesting talk. It's home for people. They like trying to bring some relevant presentations that will be good for everybody with their interest. And we got Dr. Brenda Hunda from the Cincinnati Museum Center, and she's going to talk to us about not her exact fossil background, but something about the landscapes of Cincinnati. So that's Brenda.
Sure. Thanks for having me, and thanks for coming out tonight. Yeah. I was alluded to by Mike. I am a paleontologist by training, and so I'm the invertebrate paleontologist at the Museum Center. But I happen to have this side love of natural disasters. I consider myself a natural disasters buff, and I don't want people to get hurt, and I don't want property to be damaged, but I love the power of the earth. And I love when the earth reminds us every once in a while that it is a very dynamic, active place. It's very easy for us to go from dropping the kids off to the grocery store, to work, to the grocery store, to picking up the kids, to everything back and forth every day, and forget that the earth is constantly reshaping itself and that we sometimes get in the way, right? And so when things like this happen on Columbia Parkway, it just is a wonderful reminder to me of the geological processes that are happening on our planet, because people tend to think that geology happens somewhere else or a long time ago, right? So when you hear about landslides in California or the earthquakes, you're like, well, yeah, I don't live in California, right? Like, so we know that there's these hot spots of geologic activity, but it actually happens everywhere, and we happen to be a hot spot for geological activity here in Cincinnati. So if you've grown up here or lived here for a long time, I'm a transplant. I've lived in Cincinnati for 21 years. You'll know that we have a lot of landslides, what we call, geologically speaking, mass movements. And it doesn't take a whole lot to actually generate one of these, but it is a function and a consequence of both landscape evolution over 450 million years and human behavior. So we're going to really lay down sort of why the geological area here is so good for landslides and why this is a battle that we keep coming up with. Now, I am not an engineer, so my job tonight is not to design your pier wall for you in your backyard. Sorry. I can point you to some resources and some people who can help you do that, or have answer some questions if you have concerns, but I'm going to tell you why it is that we have all of this activity here. So I think people not from Cincinnati are very surprised to know that Cincinnati is actually one of the top 5 in the 80s, top 10 per capita costs of landslide damage in the United States. We're in Ohio. What in the world could that possibly have to do with anything? When we look at the national landslide map, oh, it's not going to show up on the TV, and we see the red spots, there's a couple of things on here that we can pretty much pinpoint where we're going to see a lot of landslides. Ooh, thank you. Oh, this is fun. I haven't used one of these. I love it. I'm a martial artist. I have a 2nd degree black belt, and I do staff. So I'm looking at this already as what weapon, how can I do this? Okay. So of course, the coastal regions here are going to be really important. The Rockies, the coastal sands and gravels that they have all the way up the West Coast. They're very soft, they're pretty young, maybe 35 million years maximum, not lithified, ocean waves coming up. It's also a tectonically active area. So we get a lot of landslides there. We're going to be seeing a lot more landslides in this area after the wildfires, right? When we denude the landscape, water comes in, it's going to rush all that stuff out. Unfortunately, LA happens to be right in the middle between the mountains and the ocean, which is exactly where the erosion wants to go, right? It wants to go from an area of high to an area of low. So unfortunately, they're kind of in the way of what the Earth would normally do. And then, of course, there's going to be areas in here like in the mountains, in this region here that are going to be really high with landslide potential, a lot of altitude there. The Appalachian Mountain Range is a young mountain range. We're actually going to see how it developed. It's very important to our landslide story, actually. We can expect to see a lot of landslides there. And then here we are right here in this little tiny red zone, okay? So when we think about California landslides, these coastal, fairly young, not fully lithified sands along the coast. I actually lived in Southern California for 5 years and got to witness somebody's back porch falling over the edge of one of these cliffs while I was on the beach. Very exciting. We can think about the mountainous regions. You know, the Earth, whatever it brings up, it has to take down. We've had mountain ranges that have gone up and completely eroded away that we didn't know existed, that we don't see anymore. This is what the Earth does, right? It's recycling its materials, and gravity is going to help along the way. And then, of course, the Appalachian Mountain Range, we're going to see a lot of types of big landslides there. And then finally in our region with a little bit of Columbia Parkway and other areas. River Road, some of you may be familiar with Elberon. Some of you may be familiar with some other areas that have a lot of landslides. And so Mount Adams, yeah, that big 1982 wall there that they have holding Mount Adams up, right? Largest mitigation wall, most expensive at the time, $30 million in the country, yeah. That has its infrastructure all to itself. It has a tunnel that goes behind there so that they can tighten the bolts, and it's just really a lot of fun. So we're really going to focus on two main time periods in the geologic time scale. We all know that the Earth is 4.57 billion, right? Same as the rest of our planets. And if we just focus here on the upper 600 million right here, this zone is getting expanded here to the 600 here, okay, million. We're going to focus on what's known as the upper or late Ordovician, somewhere around the 450 million year time frame. Now, normally I would go into a discussion about the animals that lived during this time in the ocean because Cincinnati was under the sea. We're going to talk a little bit about that. I don't think I have any fossils in this talk. Shame on me. Okay. And then we're actually going to skip sort of all of this. So all the way up to the last about 2 million years. So this is this zone right here expanded out up into the last 2 million years of geologic time to talk a little bit about, yeah, just like that. In fact, between about 450 million to 2 million is a gap in geologic time in Cincinnati. So there's about 500 million year gap in the geologic record in Cincinnati. We have other rocks in Ohio that fill in some of this gap here, but we have no Mesozoic anywhere in Cincinnati or in Ohio or in Indiana or Kentucky for that matter. So no dinosaur age deposits here, even though I'm sure dinosaurs did live here because they lived everywhere, right? Okay, so we're going to start off 450 million years ago, and we're going to go way back. This is the thing I love about geology and paleontology. It's kind of like the only time machine that we actually have. And we can reconstruct these ancient Earths and ancient environments using the fossils and other techniques that we use. So this is the ocean, this is the world about 450 million years ago. Thanks to plate tectonics, ocean configurations have changed, continental configurations have changed. But here we are, right here in the southern hemisphere, about 20 degrees south of the equator. So our continent, North America, was pretty much predominantly southern hemisphere continent, except for the last 250 million years. And you can also see that we're blue. So the blue, of course, is ocean. So during this time in Earth's history, most of the continental land masses are covered in a shallow tropical ocean. This is an ocean that would have come over the central core of what is North America. We don't call it North America, even though there's some outlines here. The Great Lakes are here. They're only 14,000 years old. James Bay and Hudson's Bay is there. Greenland is there. It's just to give you an idea of the general configuration of the continent. But we don't have yet any eastern seaboard. There's no Florida, Texas, nothing. There's no western seaboard. It's just a central craton right here. And the green part is the stuff that's exposed. That's land. Okay. And so just to give ourselves a little bit of orientation, Siberia is our closest neighbor. I'm not going to make any political jokes, but I think you know where I'm going. Baltica is our second closest neighbor. That is Northern Europe and the Baltic countries, right? So Norway, Sweden, Denmark, Finland, parts of Northern Europe. That is actually going to collide with us to create the Caledonian Mountain Range at about 360 million years. So that's going to actually become part of our continent for a little while and then reseparate. We have this very large megacontinent called Gondwana. Gondwana is a predominantly southern hemisphere continent. It's a major theme in Earth's history. It tends to stick around for a really long time. And it's made up of all the A's. So Africa, Antarctica, Australia, South America, a little bit of India, some of China, Madagascar's in there as well. Okay, so that's Gondwana. Gondwana is a major driver, FYI, for our glaciations and our ice ages here on Earth. And then we have this little tiny area here called a volcanic island arc system. And this is where New England and Nova Scotia are located. Yeah. Might be a nice place to go for a little vacay. But it's a little further south here, kind of the thought. This ultimately is going to collide with the eastern margin of the proto-North American continent, what we call Laurentia, okay? So because continents evolve, right, not organically, inorganically, they change, they grow, they come together, they move apart, all that kind of stuff. We don't recognize North America as a continent. Geologists don't until the Cretaceous time period. That is the time of T-Rex, where we can actually say it is a fully formed continent, right? Most of the geological additions that we need to make are already there, right? And of course, the record of those geological additions, what we call continental accretions, are the mountain ranges on either side, right? So once the Rockies have mostly formed and the Appalachians have mostly formed, right, with those collisions on the margins, we have what we refer to kind of as a North America. All right. So what's happening to give us a lot of the rocks that we have? Starting at about 470 and kind of coming to completion at about 450 million years ago, we had the birth of the Appalachian Mountain Range. Now, the Appalachian Mountain Range is a three-phase collision, what we call a continental accretion, on the eastern margin of the United States. And the one at 470 million into 450 is the first one, known as the tectonic orogeny. Orogeny is a fancy word for saying mountain building event, okay? So we're making the base. And so there's that little terrain, that volcanic island arc I told you about with Nova Scotia and New England in there. Coming in, there's some little volcanoes, boop, 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 and slamming into the eastern margin of Laurentia. So this would be like taking Japan and sticking it to the side, okay? This is going to be a very large mountain range. I mean, you know, Rockies, possibly higher. It's brand new. It's also naked, right? At this point, there is no life on land, or very little, and nothing completely inland. And so there's no vegetation on these mountains whatsoever. And because there's no vegetation on them, they're subject to a lot of erosion. And that erosion happens very rapidly, much more rapidly than, say, something like in the Rockies today or the Appalachians today, because there's nothing to protect the rock from being chemically or physically weathered. And so all of the sediment that is being shed off of these mountains gets pushed via hurricanes into our region. So here's the tectonics, the first of our collisions. This is the second collision here that's coming up at about 360 million. It's going to add parts of New England. It's going to add parts of New York State. I believe a little bit of the Carolinas are going to be here. And this is also going to swing up and hit here and create the Caledonian Mountain Range, which we share with Europe. Okay. And so we have evidence in the rocks that these very large hurricanes would come through, across and down, because they're going to be rotating this direction, down through this region, and take all of that sediment that's kind of accumulated at the base of those eroding mountains, and with huge storm waves, shove them down into the ocean, down what's called a storm-dominated ramp. So you can imagine if we go here, that this is an area of near shore, the base of a mountain range, and this is going to be a deeper area here. So all the sediment coming off of here is going to travel about 300 miles into our region. Okay? And it's going to do that through the action of storm waves and gravity, right? So if you're on a slope, the gravity is going to help take all of that sediment and make a gravity cloud. So it's a cloud of sediment that has been stirred up by storm waves and then transported down slope with the help of gravity, right, to deposit a lot of muds that we see in this region. Those muds that come from these underwater mudslides, essentially from that storm activity, buries anything that's alive on the seafloor, and that's where we get a lot of our beautiful fossils from, is these continuous pulses of mud from these storm waves that come in and bury all this. Okay. Consequently, you get accumulations of mud and debris in very deeper water type environments. Okay, now when I say deep water, I'm not referring to like abyssal plain kind of stuff. This is really only about 150 feet in total depth. So it's very shallow relative to the ocean today, but it is the deeper part of the ocean where waves cannot penetrate to hit the bottom of the floor. But up here where it's shallower, okay, we can penetrate with waves and hit the bottom of the sea floor. And that concentrates all that shelly debris and then takes that mud and shoots it downslope. Okay, so I like to think if you took a chunk of Cincinnati mud, which I'll show you a picture of in a minute here, and put it in a washing machine at your house, right? The cycle eventually would get rid of all the mud and that would go down slope or down your drain, but the shells would be concentrated. And those shells form limestones. So if you take a look at these beds here, right, these are all the muds that are coming off, those mudslides, and then these are the limestones that are coming in and being concentrated by the waves of the storms. And if you actually look at these muds in cross section, and you can see these at the cut in the hill, there's sort of patterns in the way the rocks are layered. That's a reflection of climate and also a reflection of sea level change. So scientists, geologists can use that to understand what's happening to ocean depth in this region. But what's really important for us here in terms of landslides is this shale right here. Okay, all that dark stuff that you see. When it is protected from weathering, like stuck in the hill, we refer to it as a mudstone. It is a blocky type of clay rock made out of clay minerals that is really, really hard, okay? But when it's exposed to, say it's been cut, and there's a hillside, it's exposed to weathering, it becomes very fissile and soft, like a shale. And the reason it does this is because clay minerals, which make up these rocks, are known to engineers as inherently weak materials, right? So clays in here are lined up like pages in a book, right? And they attract water, so they're hydrophilic. Their charges actually attract water molecules to them. When the water molecules attach to the clay mineral, right, what happens is that they spread those sheets of clay minerals apart from each other. And when you spread those sheets of clay minerals apart from each other, you lose friction. And that's the force that holds the things together. So if you've ever gotten a book wet, right, you know that you're never getting the pages back together to the way it used to be, right? That's exactly the same kind of thing with clay minerals. Once they get wet, they splay out and they lose contact with each other. And then that whatever forces, frictions that are holding them together in place are now gone and you basically make mud, okay? So this inherently weak material that you see an awful lot near the surface, this is the cope here, right? Near the surface, this is the shale, and then here where it's deep, it has a bit more structural integrity. It just basically falls apart, right, when it gets wet. And you can go play in the mud, basically. It's 450 million-year-old ocean bottom mud, which I think is particularly cool, but it's very weakly cemented, okay? This is gonna have a major role in landslides, right? Because obviously, if you're building on weakly cemented material that just falls apart when it gets wet, this is kind of an issue. But it's only one part of the issue. So we're going to get back to this in a minute. And you can see that there is a lot of cope formation here in Cincinnati. So the cope formation is the formation that has the most amount of this clay material in it. And it is essentially right where Cincinnati is located. So pretty much almost at the tops of the hills, not quite, but almost at the top of every hill in Cincinnati is cope formation. It is a lot of mud, okay, in the stream beds and in the road cuts. We define the different types of formations and what names we give them based on how much shale versus how much limestone they have. And the rocks around here are predominantly shale, which means they're predominantly made out of inherently weak material, okay? So this is a legacy that we have earned from the ocean that used to be here 450 million years ago and the birth of the Appalachian Mountain Range, right? Not much we can do about that. But the second major factor that contributes to our landslides, excuse me, in this region is the glaciation that we've had in Ohio. When I first got here in Cincinnati, I was told that Cincinnati was a city of 7 hills, right? Everyone heard that? And I'm like, where are the hills? Because as a geologist, I'm looking at landscape processes. I don't see hills, I see valleys, right? Making a hill is a different process than making a valley. You get hills when you make valleys, but we're not mountain building here, right? And so for me, I'm like, it's not 7 hills, it's 3 valleys, right? Because we're down cutting, okay? And those valleys are cut through our glacial activity. We have had at least 3 glacial advances that have reached Sharonville, maybe a little bit further south in the last 1.2 or so million years. There is potential evidence for a 4th, older one that scientists kind of argue about, but the problem with studying glaciations is that glaciers are bulldozers. So they tend to destroy the evidence of the preceding glacier before them because they just bulldoze everything through. Luckily, we are at the terminus in Cincinnati of glaciers. This is why we have the beautiful hills that we have and Columbus does not, right? We are at the end and our landscape was not scraped by glaciers, it was down cut by glaciers. So I want to kind of give you a primary prep on what the glaciers did to our landscape over the last 1.2 million years by introducing you to pre-glacial drainage. This is before the Ohio River existed in this area, okay? We had a major system called the Taze River. I don't know if any of you have ever been in New York State. The Taze used to flow through there. There's the Taze-aged valleys in New York. It refers to this river that was in this region 2 to 5 million years ago, okay? And the main drainage was in the Appalachian Mountain Ranges, okay, all the way up, traveling north, out through Indiana, Illinois, to connect up with the Mississippi and down through the Gulf of Mexico, okay? In Cincinnati, we had 2 major tributaries, okay? And both of these flowed northward. We had what we now know of as the Great Miami, which flowed northward up, and the Licking. This is called the Old Licking, which came from, obviously, Kentucky, and flowed north all the way up through the Mill Creek Valley. Okay, so when you go and drive on the I-75 up the Mill Creek and you see our beautifully Army Corps of Engineered Mill Creek, right? I'm being facetious. You're like, it's very beautiful. You see, this is a really small creek, but this is a mile-wide, sometimes 5-mile-wide valley. How did this thing make that thing? Well, it didn't. Right, so we call the Mill Creek an underfit stream because it actually really didn't carve that. It's a very young stream relative to the geologic history of this region. Most of it was cut by the Taze River system, this old river that drained northward and cut all the way down. So if you think about the hills today in Cincinnati, maybe go from Price Hill to Clifton, and just think about that line of hills. minus a few quarries, right? That was the level that the land used to be before the Tays started carving through it. Okay, so everything below that has now been carved out. Okay, so the Tays would have carved out probably about half of that height down to where we are today in the modern. All right, very happy. Water's flowing. It's getting out of the system. It's going to the Gulf of Mexico. All good, except that we throw a huge ice block in the way, known as the Kansan glaciation. So this is the first of three advances that we have coming out of Canada. I'm Canadian, and this is how we're going to take over your country. It's going to be very slow, and probably not for another 100,000 years, but I'm also an American citizen, so I'll be there to shovel all the ice out of the way with you. So my toothpaste tube color there is, toothpaste color is our glacier. That's the approximate location of where it was located. We can easily see where glaciers were because they leave evidence behind, right? They leave their moraines, they leave their eskers, they leave all kinds of features that tell us, oh, that was the southern extent, and here's how it regressed back. And so, of course, this is a huge ice dam, probably half a mile to a mile thick. A big problem for water drainage. So the water has to get out of the system somehow. So the major tributary, the major section of the Tays is dammed, and it creates this huge lake called Lake Tite, which is about 2/3 the size of Lake Erie today. And then we had our own version here, right? We had both of these northward flowing creeks, or streams, but they had nowhere to go now. So what they do is they fill up basically the valleys that they carved, right? Like a big bathtub. The water's still coming up north, but it's got nowhere to go. So it has to get out somehow. And when it does, it does it in classic catastrophic geological style, right? The basin or the bathtub fills up. There's nowhere for the water to go. It creates a huge lake, which we can't actually see if you see any construction like Mitchell Avenue, anything like that. Spring Grove is built on this kind of stuff. It creates, it fills up and it creates a cut over here by Madison, Indiana, and quickly, geologically speaking, carves out the first section of the Ohio River from Madison, Indiana to the Mississippi, and causes a huge drain and gets that water all the way out. I would have loved to have been in a helicopter to see that happen. But as it does that, because it's such an energetic, catastrophic situation, it carves a channel up near Hamilton to connect the Mill Creek with the Great Miami, and it switches the direction of the Great Miami to go southward now to create what we refer to as deep stage Ohio River. And that helps get the water out. You can still see that channel connection just north of IKEA from satellite imagery. It's still there. What's very cool about it is because that water is rushing so quickly, it actually carves those valleys that the Tays started 100 feet deeper than what we have today. So it just made a huge valley under there. And we refer to this as Cincinnati as a southern city because we would have been south of the proto-Ohio, right, or the deep stage Ohio. Okay, all right. So now we have a new system of flow to get water out of the system, but round two comes in, known as the Illinoisan glaciation, 400,000 years ago. And round two comes down, okay, and once again blocks the northward flowing licking, right? So we're still flowing up here, but because this is going south now, it's not blocking anything. And what we're doing is we're melting the glacier and we're putting lots of sand and gravels filling up that void in the Great Miami. And the Little Miami too, by the way, which ultimately will become our second aquifer of drinking water, right, for the city. Also a great source of water for beer. This is why the beer is so good in Cincinnati, because it's all glacial sands and gravels. All right, kind of the same story happens again. We fill up the bathtub, we've got nowhere to go. We break the dam at Anderson Ferry and carve a new path from Anderson Ferry out to Madison for a second section of the Ohio River. to get that water out, okay? Now, there's a little bit of debate exactly about how this goes, but some geologists think, and the landscape tells us this had to be the case, that the Illinoisan kind of went a little bit back and then it came for another advance, which happens with glaciers. They retreat and advance and retreat and advance. And that would have been close to what would be this dotted line here, close to downtown Cincinnati. So the licking would have actually flown in here and basically had to cut, because this was all blocked off, had to cut a new channel of the Ohio from downtown Cincinnati to Anderson Ferry to give us that completed section of the Ohio River in this region, okay? And so we basically had a three-phase section of the creation of the Ohio River here in this area, okay? So the third advance, which is the one that I should mention, by the way, that the Illinoisan is really cool because it is really the sediments that we see a lot of in the region. So if you've ever gone to River Downs on 52, the bluffs that are on the left-hand side, those are all Illinoisan sand and gravels, right? So they're made up of all sands and gravels. I think I have a picture on here. I'm not sure if I do. That's from the Illinoisan glaciation. If you've ever gone to California Woods Nature Park for a little wildflower hike, and you're like, where's all the sand come from? I feel like I'm at the beach. That's Illinoisan sands and gravels, right? So these are remnants of when ancient outwash rivers used to be in this area and from the melting of the glaciers. So as the glaciers receded back, the water had to go somewhere and they would outwash and create these rivers that had these beautiful sands and gravels coming through. All right. So the third one, the Wisconsin glaciation, by this time we have pretty much a modern flow regime for this area. We have this part of the Ohio connecting up to more of eastern Ohio. We have the full section of our Ohio all the way getting down the Mississippi. We have our southward flow. And for the first time, the Mill Creek flows south to connect up, and the Licking flows north, but to connect up with the Ohio. So for the first time at this phase, those two systems are now separate, okay? And they're filling up a lot of this with sands and gravels that kind of fill the valley up to our modern levels and create the beautiful aquifers that we have for like the Bernard soap factory. If you're ever wondering why it's in Mill Creek, it's using the water that's down there. Sands and gravels are beautiful natural filters for excellent water. So we have excellent water here in Cincinnati because of our glacial history. In addition to, you know, the EPA and the Cincinnati Water Works and all the things that, you know, have a long history here and do wonderful things with their water. And if you go around Cincinnati and are lucky to sort of see certain exposures, you can see the glacial history is here. This is the glacial map of Ohio. And you can see they're color-coded based on types of deposits and their ages, but you can kind of see where the last Wisconsin glaciation or lobe was. It was a two-part lobe. And that's because as glaciers melt back, they dump the sediment that they've entrained in the ice, and they leave a record of their recession, right? So we can see, based on the terminal moraine here at the bottom, where the furthest extent of any of these glacial advances are. There's the Illinoisan there as well. So
all those blue bands are moraines?
yes. Yep, they're all moraines. Dumping all the way back ultimately. So glacial maximum here was about 18,000. For the Wisconsin, it started dying back after that, created the Great Lakes at about 14,000, that's how old they are. So it took about 4,000 years to get out of here. I mean, 4,000, yeah, 4,000. That's right. Okay. Also, the fact that Cincinnati itself, Losantaville, is where it's located is because it's on a Wisconsin age terrace, right? That is dumped sediment from the last glaciation, and it puts it high enough above the river that in relation to things like Columbia Tusculum and Sailor Park, would get flooded much more frequently, downtown Cincinnati only gets hit by the biggest things, right? Like 37, 64, that kind of stuff. Not seasonal, you know, or annual flooding. So that's one of the reasons why Fort Washington was put where it was because it was high up above the river that Not only was it a good strategic point, but it didn't get flooded every year. So thanks to geology for that. Okay, so what does all of this mean? Well, the glaciers give us what we love the most about being here, right? But everyone comes to Cincinnati, they're like, ooh, this place is pretty. Who knew? Because we have these beautifully carved valleys, right, that give us these fantastic slopes. The problem is that they're slopes on inherently weak material. See where I'm going, right? And so there's a lot of infrastructure, right, like the Mount Adams Pier Wall, that is needed to hold up these hillsides. And once you know what to recognize them, you know, then you're like, wow, man, there's like a lot here. The city is actually getting very good at hiding them, making it pretty. Let's put a sidewalk and a fence over here. You don't know that there's $1 million pier wall beneath you holding this whole thing up, right? They're getting very, very good at it. For a long time, it used to be in our geological history that we were focused really on cleaning things up, but now we're getting much better at preventing them in the first place. And landslides are fascinating because they are the only natural disaster that you can prevent. You can't prevent a flood. You can mitigate a flood, but you can't prevent it. If you mitigate the flood in Cincinnati, someone's going to get it downstream or someone's going to get it upstream, right? The water has to go somewhere. So there's always flooding somewhere. But you can't prevent earthquakes and hurricanes and tornadoes, but you can prevent landslides, right? And so we're getting much better at being able to do that. And this is really the big problem that we have for most of our landslides in Cincinnati. And that is the natural process of weathering and erosion. So I mentioned to you that the rock around here is hard as a rock if it is in the hillside and is not exposed to weathering. People put piers down there and build high rises on it, right? It is strong. So you can build structures on that. But once you build on a hill slope that is exposed to weathering and erosion, that's when the real problems come in. And so over time, all of that rock gets exposed. It creates mud and bits of rock. Bits of limestone, vegetation gets mixed into there as well, and you get this thing called colluvium, which is a clay-rich deposit from the clays that we have in our rock that forms on many slopes that we have in Cincinnati. So if you look at the cut in the hill, or if you're going down the 471 into northern Kentucky and you see all those hillsides, you see that there's mud that's kind of, and debris that's kind of accumulating on the slopes, right? That is the weathering erosion process. And it's heavy, right? And it can accumulate for a very long time. In fact, the Columbia Parkway colluvium accumulations were 6 feet thick, and that took about 80 years. So they scraped it, they built the second lane of Columbia Parkway in the 1930s. And so by about 1930 to about 2020, which is 90 years, it had a 6 foot thick accumulation. And at some point, that weight is going to be too much and it's going to fail. So the reason why we're seeing a lot of Columbia Parkway coming down, because it's reached its maximum hold, meaning there was not enough friction to hold that material on anymore on that slope, okay? And that's because slopes and materials have what's called the angle of repose, right? This is the angle that a material can hold based on its grain size. So you could imagine you go to the beach, you fill in your bucket, you make your sandcastle, it's completely dry, and every time you do it, you pull it up and it makes a pyramid, right? That's the angle that material at that size is stable at. It's going to be different for gravel, it's going to be different for pebbles, it's going to be different for sand. If you add a little bit of water to your bucket, you can get it to hold and make a sandcastle out of it. If you add too much water, it comes out as a wet slurry, okay? So the angle of repose is going to be a combination of the grain size of the material and the slope that it is on, and whether or not gravity and friction can hold it in place. At some point, if it still accumulates, friction will no longer be able to hold it because it's wet and heavy, and gravity is just going to let it go. So that's really what a lot of our sort of landslides especially the ones on Columbia Parkway, are kind of made up of. Now, that's not to say that that isn't the only thing that triggers landslides. Certainly, we've had massive landslides. The ones I described for you before are called translational slides. They tend to be small, confined. They might interrupt your traffic flow in the morning on your way to work. Columbia Parkway shut down for a few days while they clean it up, right? It's not a huge deal. But we do get rotational slumps in this area where the scarps or the lines of weakness are way, way down in the rock layers and take whole hillsides down with them. An example being the Clifton Avenue slide in 1972, right? Some examples, Columbia Parkway had a major one. They had landslides in Columbia Parkway as they were building Columbia Parkway. 1930, and there's a landslide. That's what's called the scarp right there. Okay. And so these, like the river road example, are where the lines of weakness are like feet down in the substrate and the whole thing is moving. And that's a different geological setting than, say, a translational slide. But those are the ones that take out apartment complexes and buildings and people's homes and stuff like that. So what we do, unfortunately, is that we take an already inherently rough situation where we have inherently weak material on very high slopes. These are not like gentle slopes. Our hills are like this, way, way too steep, okay? And we put stuff on top of it. We do what's called loading the head, right? So we build an apartment complex on there. This, by the way, is a very interesting landslide because it was caused by historical quarrying activity. On the hill up here is the Fairview Park, and they were quarrying to get the lime out of there and dumping all the shale over the hillside, right? 100 years later, we forgot that we did that. All that rock and shale is not only inherently weak, it's now completely removed out of context. It's no longer attached to anything. It's just a big mud pile. And then we build some things on it and it fails, right? So quarrying, and this what we call cut and fill, where you cut a hill and then you use that to fill the other side of the hill to maybe make more land for subdivisions and things like that, is a dangerous practice. And a lot of developers do that. It's a function of historical quarrying activity or development. It's a real problem. And if it was done a long time ago and nobody asks the questions and you don't have a geotechnical engineer to tell you the history of your land, and you would never know, right? And no one, by the way, real estate agents do not have to disclose that to you by law. So you gotta be careful. So we also do something loading the head, right? We put apartment complexes on it. We put our pools on there. Water's very heavy. We also cut the toe of the slope. This, everyone probably recognizes this over at the Newport Shopping Center. That was before they decided to put concrete on it. What's it called? It's a special name, but I can't remember. I'll think of it. It's a spray concrete. Looks atrocious. By the way, it's going to weather away as well. It's not impervious to the natural forces of our planet by any means. But what's that? No, I got to think of the name, but it's neither here nor there at this point. But it's just spray on concrete. They do it a lot in California on the hill slopes too. It's a Band-Aid, you know, it's just, yeah. And so you can see if you're living up here that you might like be slightly concerned.
So they're doing both there. They're loading the head
and cutting the toe. Yeah. Oops. Smart. Another way, so the cut and fill, this is Columbia Parkway was a cut and fill. They took it was at one lane at one point. They took the hill, they cut it off, they put the second lane down, it failed, still fails. And then of course, removal of vegetation, right? So most of the vegetation that we had in this area was removed for supply. And when you remove vegetation, it's not, if your slip surface is way down in the ground, trees aren't going to help you. But if you're trying to stabilize maybe the upper 6 feet of the profile of a hillside, trees do a lot of great things. First, the roots are really important for binding the soil profile. And secondly, they drink a lot of water, which is what you want. You want a natural way to get the water out after a rain, and vegetation is a perfect way to get the water out, right? So removal of vegetation is going to be a major problem. All right, so what we end up with is the perfect recipe for disaster in Cincinnati, right? We have our ancient marine sediments, which love water. They're hydrophilic. They attract water to them. They separate. They create these inherently weak materials. The grains in that rock are no longer really touching, so there's no friction holding the sediments together. They basically become mud on hill slopes. Okay, so we have an inherently weak material from our ancient ocean that was here 450 million years ago. We add that with naturally carved slopes from 3 glacial advances in the area that didn't just carve the slope a little bit, but carved it at very high angles, really beyond most angles of repose for most materials, right? We then add human activity on top of that, where we cut those slopes even more. We add things to the top, and create very dangerous conditions. And then one more thing we can't do about is that we live in a humid continental subtropical climate, which means we get a lot of water, and we get a lot of rain from the Gulf of Mexico. We are right smack in that weather system between the colliding air masses over the center of the United States, between the Gulf of Mexico and cold Canadian air, and we get a lot of precipitation. And water is bad when it comes to landslides. It's heavy, and it also is a lubricant. So whenever we have really heavy rains in the spring, we end up getting a lot of landslides. And so these 4 factors that we have here, 3 of which we can do nothing about, is our recipe for landslides. Hello. Right. Okay, so when we look at our landslides today on our US map, we can see that we have right in here sort of our 3 valley systems. Our Great Miami, our Little Miami, and our Merrill Creek Valley is where most of our high slopes are in the area. That is a high landslide area. Now in the 70s, Cincinnati was top in terms of cost per capita for Hamilton County in the entire United States in terms of landslide mitigation, right? I don't know what it is today. I can't find a stat on it, but I think California probably beats us now. But I can tell you that the city does put a lot of money into landslide, the city and the state. It's a dual situation. A lot of money into landslide mitigation. And so you can think about how expensive that $10 million wall was on River Road. There's $1 million wall right as you come in on the I-74 before you split off of 275. Good Sam Hospital has $1 million wall holding up, what road is that again? Remind me. Dick Smith. That wall is buried underneath the ground. It looks really pretty, but there's $1 million wall under that. You would never know, to prevent it from going into the creek. And so we do put a lot of money into that. In fact, as of 2021, and the city has not updated their numbers because it's going to be higher than this, there were over 172.78 miles of structure, of wall holding the city up. Okay, so we have, in the city, we have over 7,000 individual walls of different kinds that hold up Price Hill, Elberon, Mount Adams, Clifton, all of Columbia Parkway, all along the river, because rivers just cut and they cause earthquakes. So that's a pretty amazing stat. And I know it's going to be more now because the River Road and other ones have been built since then. So if you haven't had a chance to see a documentary that I was able to participate in as the geologist, I'm just going to give a little plug for that. We did make a Living with Landslides documentary. You can see it here at this website. It's a fantastic documentary by Laurie Quinlivan that shows the geology and the history and goes a lot more deep into engineering and city policy with related to landslides and landslide disasters. Because right now there is no insurance. There's no landslide insurance. It doesn't exist anywhere in the country, right? So if you have a problem, it's a homeowner issue. So there's all those kinds of discussions about that. I don't know if you guys remember the Mount Adams slide that happened, I guess I want to say maybe 7 years ago, it was pre-COVID, that took out City View Tavern, beneath City View Tavern there. Yeah. So they're highlighted in here as well. And so it's just a really fun. I had fun. I had a lot of fun. Cincinnati view of landslides. All right. Little light, viewing before bed. Nothing to scare you, with it. All right. Thank you very much. I'll take questions.
Let's start with the ripple dome that used to be here on Cincinnati
Ripple dome.
when the Appalachians formed.
Mm-hmm.
There was a ripple.
Oh, you're talking about the Cincinnati Arch and the Basin Bulge complex.
Right.
Yes.
And that was scraped off
Yes.
to give the geologists their history of the world.
Yes.
Across Cincinnati.
Yes.
Did that occur on the glacier that you mentioned? That was the fourth one that,
No, so we didn't go into the Cincinnati Arch.
yeah.
When we were, I'll just back up a little bit. When we were talking about those 3 collisions on the eastern margin of Laurentia, you can't have collisions like that without stress in the interior of a landmass. And so what happens is the landmass on the inside buckles to accommodate the stress that's happening on the edge. And so it creates what's called a basin and bulge complex. And so if the stress is coming this size, it causes the crust to down warp like this. And then it has an equal reaction to an up warping in the interior of the continent. The down warp would be like in New York State, and the up warping is here in Cincinnati in the Ohio, Kentucky, Indiana region, and it's known as the Cincinnati Arch. So the Cincinnati Arch is a tri-state geological feature, and the top was cut off of it, not by the glaciers. It happened much earlier than that. It happened over the course of 250 million years of non-deposition and erosion. So after we were an ocean continent, we became a land continent. So all the rock that was there was eroded away by rivers and streams and natural erosion. All the things. And so it took about 250 million years to do it, right? The glaciers have taken a little bit of the top off, but it is not, it's not related to the building of the Cincinnati Arch. And once the Cincinnati Arch was cut off, it allowed for the oldest rocks in the bottom to be in the center and then progressively move younger out of Ohio, Indiana, Kentucky. I don't have a visual for you. I actually probably do on my flash drive if anyone wants to see it, but yeah. And that explains our geology.
Does that contribute to the exposure of these weaker materials with exposure?
It would have been a little bit more flat, what we call the Lexington peneplain at that time. So most of the exposure comes from the down cutting by glacial outwash.
Okay, but
yeah, it's a much earlier, like a much longer term process of erosion to get that.
If you look at the level of Mount Adams, Mount Auburn, Price Hill,
yeah,
you look at Kentucky, it's the same.
Yeah, that's the Lexington peneplain. Yeah, so that would have been here as a flat plain, essentially about 5 million years ago before the Tay started cutting it. Yeah, and washing it out. Yes.
Over along 275 in northern Kentucky, along that commute, kind of in the Licking Valley.
Yeah.
The valley that's just to the west of that as well. There's multiple places along the highway where we've had kind of these miniature landslides. And the rain we had this spring didn't seem like it was that excessive compared to past years. Is this another situation where it's just a matter of it's built up since the amount of time where they cut 275?
Yeah, I mean, without knowing it and without seeing it, yes, most likely, right. It takes time for that colluvium to build up, and then eventually at some point the weight of it the gravity will take over.
It just seems weird in multiple places. It was pretty rainy in the spring, but it wasn't.
As bad, like, yeah, like 2014 was really bad. Like a lot of action going on. Yeah, it probably was just at that spot, there was an extra weight. Without me looking at it, would be my guess. And buildup of the colluvium. Yes.
Oh,
Oh,
so,
fun.
I mean, your main course of study, is that what brought you into this? I mean, is this how we know these things happen?
Yeah. Well, so I love anything to do with the Earth. I mean, by the way, I like other planets too. I did teach planetary geology for a little while, so it's fascinating. And I watch all the astronomy that I possibly can. But as far as living on this planet, when I came to Cincinnati, I came for the fossils, but I also wanted to understand, because I also love looking at landscapes and how we get what we get when we go, I'm always looking at the hills and the trees and all that. I wanted to learn all about that. And there was no place where I could synthesize all of the geology in one spot. There was no resource that said, this is how we get from here to here. And so I was like, I got to make it because I need to be able to tell that story. And so, yeah, I wanted to put it, there's no place other than what I'm giving you that puts all of this together in one spot. Yes, I've thought about it. I have several that I'm thinking about. Yeah.
There's an aquifer underneath a lot of counties in this area. How would that?
So are you thinking like, that's all groundwater flow?
From the glaciers? And or changing direction?
I don't know, like, the history of the hydrology of the subsurface other than what I know about the creeks, like the big valleys.
Well, the big aquifer under the Mill Creek Valley.
Yes, that one, and then the Great Miami.
All the breweries.
Yes, those ones are the sands and gravels from the outwash of the glaciers. Yes, and then the Little Miami, and Norwood Lateral, by the way, is also a glacially carved valley as well. All right, we tend.
Is that an old path of?
A glacier, yeah. I can't say this like 100% of the time, but if you're driving up avenues like Queen City and all of those, Norwood Lateral, the humans tend to put roads and paths of least resistance, which usually means that, and railroads, which probably means that that was a tributary to the main Tays or to the Licking at some point in its history that would have funneled down into the Mill Creek Valley.
So right over the hill back here where Lunkin Airport was one of the valleys of the Tay.
Yes, it was. Yep. And you had a question back there?
Given our position you have here today, it's just magic. What is your crystal ball say?
Oh, where's that going to be? Well, yeah, it'd be great if I could pick that. I don't know, but I do have a friend in the transportation engineering department at the city who goes out with me every once in a while, and he shows me all the real cool things that are happening in terms of landslides. So I haven't touched base with him for a little while. I'll have to ask him. River Road, of course, was huge, but that was a subsurface slip, meaning that you could see the sidewalks beginning to crack and the road beginning to crack on River Road, and the houses on that side starting to, which is a big lawsuit. But that wasn't like super note, like these translational slides are much easier to see. A big one? Oh my God, maybe, or all the way over in, did you see, so when you're looking at Covington and you look over here, the hillside, that's that new subdivision, they completely denuded the hill there, took all the vegetation off to build it. So that's my prediction. How about that? They're building, I don't know if they have a geotechnical engineer because they're not required to by law in Ohio. I don't know if that's the case in Kentucky, but denuding that and then building subdivisions on top of that slope are two of the bad things you can do to promote a landslide. So I'm going to put my money on that, unfortunately. Yeah.
The go back in the slide, maybe one or two. Let's see. This one more.
Yeah,
Yeah, okay. Bottom right.
You wanted to go to
48, yeah.
Yeah.
Yeah. The observatory was on Mount Adams by 1845.
It's just cut out of the picture. That's the same picture.
Oh, is it right over there? Oh, yeah, yeah, I see it. I see it. It was just cut out of the picture. I was interested in the naked landscape. Yeah, yeah. That's cool. That's a classic.
Mount Adams. So in our backyard, we had a 30 or 40-foot tall stone wall,
Mm,
which fortunately, I mean, I haven't lived there since 1965,
yeah.
so I think it's still there. And the church there, which you had a picture showed, you had
Oh,
Mount Adams.
Yeah, yeah, in the church.
And
Yeah.
That's a monstrous wall.
Yes.
Sure.
That pier wall. Yeah.
Probably behind there is that formation you're talking about.
Yeah. Oh, yeah. That's all cope.
It's all code.
Yeah.
So that wall is protecting it and keeping the church up.
Keeping everything up there. That's a huge, that pier wall is, if you ever have a chance, there is some information on the web about that wall and its construction because it actually has like a little city behind it. So it has a tunnel that they have to go into and the bolts. Oh, you're talking about that one.
Talk about the old wall around
Oh, okay.
the church. No.
Yeah, okay. Was it a WPA wall?
No.
It was earlier than that?
They had to build that in 1860.
Okay, it's earlier than that. Because a lot of the WPA walls that are built here still are awesome.
Yeah, my grandfather
Like they're solid.
built horns with that.
Yeah,
Columbia Park.
they don't move. Yes, they don't move. They are amazing.
They just do-
Yes, we don't build walls like that anymore. So,
Is the climate like freeze thaw or, I don't know what the climate was like back 400 years ago?
yeah.
Was it more consistent or did we have seasonal changes just like we do now? Whether we have winter and
Yes. So back in the Ordovician time period, we were in a much warmer climate. There was no ice anywhere on Earth at the time that we were living here. So we wouldn't have had that kind of seasonal, as much of a seasonal change as we're experiencing now. But you do bring up a very good point with freeze-thaw cycles, because I haven't mentioned creep in this, which everyone kind of experiences a little bit around here with freeze-thaw cycles. It's kind of like when your hillsides start to slowly come down and your curb disappears, you know, or your trees start to have the bend that goes up like this because they're trying to right themselves to the sun. Those are all signs that your hillside is slowly coming down, and eventually it will just give, right? Like it's going to come down, going to kind of slowly, and it's in part because of the freeze-thaw cycles of Cincinnati. So there's the expansion of the water in the soil, and then it contracts, and then it loosens upon expansion, and then it contracts, and then it loosens, and then it contracts, and then you do that down the hill, and you get, you know, that creep. So signs of that are signs that you've got a hill that's coming down and that it might give way at some point. So we didn't talk about creep, but.
You mentioned planetary geology. I'm thinking other planets like Mars, there's evidence of landslides.
Yeah.
Other than the human factor causing them, a lot of the same processes are happening with water movement, we saw annular reposes, why those are happening or had happened in the past.
Yes. Yeah. And I think, of course, we know that the Earth and its processes here are the ways that we can work to interpret some of the processes that are happening on other planets, right? So what we learn here, I think the fundamental laws of physics and chemistry apply, although you might be dealing with methane versus like water, but you know, generally speaking. So a lot of the landslides on other planets. Didn't they recently see landslides on Titan? I thought I saw a documentary on that. Anyway, I'll have to look at which one, which moon it was. But yeah, you can use these kinds of processes to look at what's happening on other planets as well. Yeah.
It just doesn't fit it.
What's that? Oh, yeah. Yeah, I think people, yeah, people think that geology is, when we think about like how a river carves a channel and it meanders on a day-to-day and it takes a while and everything's slow and steady. No, most of the most interesting things in geology are catastrophic. Think about the Scablands and the Grand Canyon, all the things, not of biblical proportions, don't get me wrong, catastrophe, but in terms of events, things can happen very quickly. And did you guys see the landslide in Sweden?
Yeah.
Whew, you can watch that actually on video coming down. That is massive.
It's the Nepali coast in Hawaii. That came down 85
That was a tsunami.
miles out. Would like to see that.
Yeah, that creates landslides can generate tsunamis when they're big enough, like the Hawaiian Islands losing like a section of the mountain.
Well, you know that if it wasn't for people, they wouldn't be disaster.
No, they would, exactly. They would be the earth doing what it's supposed to do. Right. It's just the earth doing what it's supposed to do.
Tree falls in the forest and nobody to hear it, does it make it sound?
Now he's going into philosophy,
Yeah,
right? Thanks, guys, for coming out tonight. It was a pleasure. Yeah.